So hello again. Made this video to try to show the connection between a law that we've seen before pretty recently, and that's called Faraday's law of induction, and a very similar version of that goes by the name Maxwell's law. It can be kind of a confusing name because Maxwell's laws are also used to describe the collection of all of the important laws in electromagnetism. They collectively are known as Maxwell's equations. But the one that in particular goes with Maxwell is the one we're going to deal with here. So I'm going to do a quick recap of Faraday's law because the Maxwell law is very, very similar to that. So with Faraday's law, we had some situation where we had a changing magnetic flux. So this could be any situation at all. We could move a magnet around. We could take a wire, a current carrying wire that has magnetism, and move it around. And anytime we do that, in any region around it, we would find that there is an electric field being created. However, in order to describe what that field would be like what magnitude, what direction, you have to have enough symmetry that you can actually apply Faraday's law. So let me write Faraday's law. On the AP reference sheet in my class, I numbered it number 58, and it looks like this. E.dl, in some textbooks you'll see that written E.ds, equals the negative of the rate of change of magnetic flux. Either of those is also called an EMF. So things that make charges move are sometimes called EMFs. Well, electric fields make charges move, and so we could consider that an EMF. But this is how we describe the form that EMF takes. So here's a situation. Again, this is the only situation with enough symmetry for us to actually carry out this calculation. It's not that's the only time that we get an electric field. It's just that I don't know what those fields would look like or how big they would be or what direction they would point because they don't have nearly enough symmetry to deal with them. So here's my magnetic field. And I'm going to say something is causing that magnetic field to change. Typically, with a round region like this, we're looking down the core, the tube, if you will, of a solenoid. And inside a solenoid is a pretty uniform magnetic field, aka magnetic flux, if we include the area. So everywhere inside there, and also everywhere outside of here, there will be an electric field created as we are changing the magnetic flux. So in this example here, I'm just going to choose a point out here. We usually name our points P, and we'll say, okay, that's where we want to describe how big and what direction the electric field will be. So let's say this is some distance, we'll call little r, and we'd like to think of little r as a variable so that, if I moved point P closer or farther, I could do that. Now, in the derivation I'm going to do here, I can't move it anywhere inside of the solenoid. So as long as we're outside the field. If you're within the magnetic flux, the law still works. You just have to make sure you apply it correctly. So that was dealt with in the previous video on Faraday's law. I'm trying to do a recap, although we're already almost 4 minutes into this and I've not really done much. So in this form here, on the left side, this is called a line integral of E.dl. Line integrals mean, imagine you're going around a path or a line. It can be a curved line. And again, you have to have enough symmetry for this to work. And so the path in this case here would be a path that goes through point P and a path at which anywhere on that path I should be able to say is equivalent point to any other place on that path. This is why we're looking for symmetry. What kind of shape provides a path around it where every point on that path is basically equivalent to any other point? The only shape that works for that is this circular shape here. If I drew a square, I could be close to a corner or farther from a corner. But circles don't have corners. So here's the path, and we always draw a little path. When we did Ampere's law, we called it an Amperian loop. It's just a loop, a circular loop, or a curved line, if you want to call it that. So I am basically describing how strong the electric field will be anywhere around on this point, or on this line here, a distance little r away. So over here, what this means is, imagine going around this and say, okay, we're going to have an electric field there. we're going to multiply it in a dot product kind of a way with the short little length of the path. So we're going to break this into a bunch of tiny little lengths, DLs we call them. And we're going to multiply that little length times the strength of the field. Well, the reason we set it up with this much symmetry is so that everywhere on that path, E is going to be the same. And so I can imagine pulling that out of my integral. It's not a variable. It doesn't have to stay in the integral. And so all I'm left with is the sum of all the little steps along that path, which for a circular path is called a circumference. So this whole left side becomes E times 2 pi little r. That's the circumference along that path. And I don't need to worry about, excuse me, a dot product, because with this symmetry, I can be sure that I am either walking in the direction of my electric field or exactly opposite. I know that the field will be along a tangential direction on my circle. So dot products aren't an issue if I have complete parallelness between my step and my field. And on this side over here, the rate of change of magnetic flux. So this would be all of the flux within the within the path that I'm dealing with. So all the flux is just on this little area here, the capital R radius, not the little r radius. So that would be the area of this circle, that's pi capital R squared, times the rate of change of the magnetic field. That represents my changing magnetic flux. And I left the negative sign. But you know what? I think I'm going to leave the negative sign off, and I'm going to do the direction part in a separate step. Okay? So now I'm going to solve for E, which is just a matter of bringing some things down here. So I'm going to divide by 2 pi little r. My pi's will cancel, and I'm left with r squared over 2 little r dB dt. And for a circular region with a changing magnetic field, that will be the strength of the electric field outside of the region. Inside the region, it would look a little different. Okay, let's talk about direction. The negative sign in Faraday's law actually has its own name. It's called Lenz's law. And we describe it this way. You say, and I realized I never specified which way my magnetic field, my B field, was changing. It makes a difference, but I think I'll just leave it kind of generic here. So if my magnetic flux here is increasing, then my electric field will be created in such a way to oppose that increase. And so what I would do is, because my increase is into the page, that's what those X's mean, my opposition to that is outside. So I would put my thumb out like I'm doing here, and my fingers curl in a counterclockwise direction. And so that would be a counterclockwise tangential direction. If I were decreasing my inward flux, then I oppose that by trying to make more inward flux. And I would put my thumb down, hard to see, and my fingers curl in a clockwise direction, and I would draw a clockwise tangential path. So at point P, it would be either down this way or up this way, again, depending on the situation. All right, so that's Faraday's law for when we're outside of the solenoid. Again, if we're inside the solenoid, almost everything is identical except the area here. We can't use all of the area of this solenoid for the flux. I can only use the area that's within the little path that I'm dealing with on the left side. It's a very important point. Okay, so let me pause here for a second. I'm going to set up a Maxwell's equation thing so you don't have to sit through all of that, and then I'll talk about what's different and also similar about Maxwell's law compared to Faraday's law. Okay, so I've basically written a parallel thing here. Maxwell's law describes how a changing electric flux creates a magnetic field. So kind of the reverse process of this. Faraday's law was describing how this magnetic field can generate and induce an electric field. We also use the word induce when we create something, I guess, in a less direct way. I should have pointed that out. Again, this is kind of a review, but we've created electric fields before in other ways. We call that static electric fields, because if you have a positive or negative charge sitting around, it comes with its own electric field. But there are no static charges in these situations. This is a totally different way of creating this field, and so we call it inducing the field. So everything is very similar. This little field region looks the same. I drew it a little smaller, but notice it's labeled E. It still has the same capital R radius. I still must restrict myself to a circular region. Otherwise, I cannot tell you how strong the field will be. There will be a field, but I wouldn't be able to anticipate what it is. I've also got a point out here still. This is a point that is a distance little r away from the center of that field. Okay. So now I'm going to claim that we will get a magnetic field generated at point P when we change something about the electric field. But I want to point out the key differences. Notice the B takes the place of E, but otherwise it's still a path integral. It's a closed path integral, also known as a line integral. And now, instead of a changing magnetic flux like we had up here, we have a changing electric flux. So where would we find a changing electric flux? Think about something you've seen before. It's a circular region with a nice uniform electric field within it, and something we can easily change. I'm going to give it away, spoiler alert. We're talking about your classic circular parallel plate capacitor. In my class in the lab, we had these big model capacitor plates from Pasco, and we could imagine, and we've actually created electric fields between there and sort of indirectly measured them. That's exactly what we're talking about here. Imagine as we're dumping charge on those plates, the magnetic field is growing between the plates, and as we take the charge off, it's shrinking. That would be a changing electric flux because there's an area that has a changing electric field. Okay? So while we're charging and discharging that capacitor, we are creating or inducing a magnetic field everywhere around it and also within it. Okay? I, again, will restrict my conversation here today to the point outside of the region, but a point inside the region is done very similarly. Okay, so we've flip-flopped the B and the E. I want you to notice another difference. Whereas up here in Faraday's law, we've got this negative sign. That's why we had to do the whole opposing thing. What opposes the change? That is important here, missing in the Maxwell law. So that means all of the right-hand rule stuff that you went through with Faraday's law, do it the exact same way, and then flip your answer. That's kind of how I do it. All right. So instead of opposing the change, it's actually maybe reinforcing the change. So if we have, in this case here, this inward flux, and let's suppose it's increasing, how do we reinforce that? We increase it even more. And so we would point our thumb, oh, sorry, this is inward. We would point it in. And so that would be a clockwise magnetic field that is induced if we were increasing this. All right. The other thing to notice is we have two fundamental electrostatic constants involved, whereas we didn't have these before. Mu naught, the permeability constant that we use for magnetism. Epsilon sub naught, the permittivity constant that's used for electric fields. To put it briefly, and this is really rough, permeability and permittivity describe in some ways the way that magnetic and electric information communicates through space. Okay, it's not instantaneous; it takes a while to travel. But you know how when I wave a magnet over here, does the electric field know it's supposed to be made over here? That has to kind of be communicated. Or how when I change the electric flux in this region here, how does the point out here know that it's changed? Something has to kind of travel or communicate that change. And that's all wrapped into these two numbers here. Now, there's a lot to these numbers, and I don't want to spoil it. If you're in my class or even not in my class and you haven't had this conversation, talk to your physics teacher about the significance of mu naught and epsilon sub naught and how it has to do with the way that electromagnetic communication happens, because we're getting at something that you're very familiar with probably. So I am not going to work through the rest of this because honestly, everything that comes after this looks identical to this as long as we're outside the region like we were here with point P, except for, as I pointed out, the epsilon sub naught and the mu sub naught are included. And obviously all the E's and B's that we have up here are going to be swapped, B's and E's. Okay, but other than that, everything's the same. And I already mentioned how the direction is opposite. So that is kind of like the best way to describe what's going on with Maxwell's law by referring it back and comparing and contrasting with what happened with Faraday's law. All right. So obviously this is a rough start. I want you to dig into the details in your textbook or wherever else you're learning this, depending on which class you're in. And hopefully you can get the rest of the details there. Or if you're in an in-person class like mine, have a conversation with your teacher. That might be even better. All right. Thanks for watching. Good luck with your physics.